Hey guys, so today we will be discussing the magnetic force and how to calculate it. So, for a point charge, the formula for the magnetic force is the force is equal to the cross product between the charge times the velocity and the magnetic field. And this is in coulombs, this is in meters per second, and this is in Teslas. And this is obviously in newtons. And this force is different from many other forces, obviously, because it's a cross product. And in that sense, it is similar to torque, which you'll recall is the moment arm crossed with the force. And if you look at the formula, you'll notice that this force is also kind of strange in the sense that if there's an object inside a magnetic field, there won't be any force done on it, any force on it if it's not moving, if it's at rest, because as you can see here, the velocity is included. So if this is just zero, it would just be zero cross with b, which would just be zero. And another thing with the magnetic force is that it cannot do work, which is the change in kinetic energy or also negative change in potential energy. And because it can't do work, that also means it can't change the speed or the velocity of the object. Or at least it can change the speed of the object. So you might be wondering, how is that possible? Because isn't force mass times acceleration? And this is just the change in velocity with respect to time. So how is it possible that the magnetic force can change the kinetic energy of the object? And the answer is because it can't change the speed of the object, but it could technically change the velocity of an object. So basically, velocity is not just how fast an object's moving. Velocity is speed and direction. In fact, speed is just the magnitude of velocity. So instead of changing the speed of the object, the velocity of an object could still change if you're changing its direction. In fact, it's kind of how the centripetal, I got them confused, centripetal force works. So the formula for it is mv squared over r, where the speed is constant. And the force would still be done on an object, unit speed's constant, if it's going in a circle, and it would be pointed inwards. And same with the acceleration. The acceleration would also be pointing inwards towards the center. And this is pretty much the same concept. So the magnetic force still causes charges to accelerate, but instead of changing the speed, it changes the direction. And now it's another thing that makes magnetic force a bit more confusing than other forces is that it's a cross product. So you kind of have to use the right hand rule a lot to getting used to finding the direction of particles traveling in. So basically, I'm gonna just call this term P. I'm gonna call this F1 as in factor one and P's product, and this is F2, just so I can make this more universal for any cross product. So basically, how you would use the right hand rule is, so your index finger would be pointing in the direction, or F1 rather, would be pointing in the direction of your index finger. F2, well, actually, I'll get to that later. And P, the product, is pointing in the direction of your thumb. And F2, some people do it differently, but some people do it just with just their middle finger. But my hands aren't that flexible, so I do it with all the fingers pointing the same direction, all the other fingers, except the index finger and the thumb. And basically, so to do the right hand rule, you have to make sure all three of these like sets of fingers are perpendicular. So it's like this. In fact, it's kind of how cross products work. So basically, the velocity and the magnetic field are making a plane together. So it's like this. And the force, or in other words, the product, if we're going to be more universal, would be pointing perpendicular to that plane or normal to that plane. So let's try an example. So let's say we have this particle here, and we want to find which direction it's moving in, and the force is pointing this way, and the magnetic field is pointing this way. So then I move my hand so that I have my thumb, my index finger, and all my other fingers perpendicular to each other. So it's kind of like the X, Y, and Z axes. In fact, that's pretty much kind of the concept, but instead it's with the direction vectors I hat, J hat, and K hat. But yes, I'd be forming the X, Y, and Z axes with my fingers. So then the magnetic field in this case is F2, so it would be pointing the direction of all my other fingers. And since the force is the product, the force would be my thumb. And then so I'd have to move my hands so that all my other fingers would be pointing this way, downwards, and my thumb would be pointing to the right. So if I do that, I would see that the object is moving into the page. So yeah, basically with cross products, so since we're dealing with 3 dimensions, we're gonna have objects moving this way or this way, up and down, but also into or out of the page. And to denote like whether an object is going in the page or out of the page, if it's going in the page, it would be just an X with a circle around it. And you can kind of think of it as the fletchings of an arrow. Like, for instance, it's like this. If the arrow is going into the page, it sort of looks like that X. And conversely, if an object is going towards you out of the page, then this would be going, it would just be a dot. It's kind of like the tip of the pointed part of an arrow. So that's one way to think of it. And also keep in mind that if it's going towards you, this is considered to be positive. And if it's going into the page, it would actually be considered to be negative. And in fact, so in 3 dimensions, so the axes kind of change. So this would actually be the positive x-axis, which is why it's positive if it goes outside. This is the positive y-axis, and this is the positive z-axis. Or if we're going to use the direction vectors, this is I hat, this is positive j hat, this is positive k hat. And in fact, I hat crossed with j hat is actually k hat. So that's an interesting thing to note about cross products. And yes, if with this, like giving them P, F1, and F2, you can pretty much find the direction for any cross product using this. And also another thing to keep in mind is that cross products aren't like normal products. So you can't just reverse this and this. It has to be in this order. So you can't say that F is B cross QV. And keep in mind charge is a scalar. That's why I don't have the vector. And yeah, this would not work. In fact, this would be equal to negative F. That's just how cross products work. But yeah, you would have to it would have to be in disorder, so it's not just a regular product. And you can also find the magnitude of this force using the formula for the magnitude of a cross product, which is just A crossed with B is equal to the magnitudes of the products of the magnitudes of A and B times the sine of the angle between them. So yeah, this is just the product of A. I mean the magnitude of A, and this is just the magnitude of B. So then the formula for the magnitude of a magnetic force for a point charge would just be magnitude of the charge times the magnitude of the velocity times sine theta. And yeah, so you'd have to sort of find them separately. The magnitude and the direction, I mean. You'd have to use the cross product for direction and then this formula for the magnitude. So yeah, this force is different in the sense that the field is not necessarily like the direction it's moving in. And keep in mind also that this formula here, F sub m is equal to qv cross with v, is only for point charges. Like if you're looking at a lone electron, if you're looking at an object which is like a continuous charge distribution, you'd have to use another formula that I'm actually going to derive right now. So let's say we have a current carrying wire, and this wire, so it's carrying current and has a bunch of tiny charges. And let's just say it's charge Q. And we can sort of think of each tiny charge as a small segment of like the total amount of charge there is, which let's just say it's Q plus Q. And so we can say that this is equal to dq, and we can and also let's say, so yeah, this is in a magnetic field, and the force exerted on this small charge, since it's a small portion of the total force exerted on the whole current carrying wire, we can say this is df. So using the original formula, now we can plug in dq for q and df for f, and then we get df is equal to dq times v crossed with b. But now we want to find the force on the whole wire, so then we would have to integrate. But before we integrate, we can actually do a bit of simplifying. So then df stays the same, dq stays the same, but then we notice that velocity is also like the change in position with respect to time. So we can change this to dl over dt cross with b. And since dt is a scalar, we can move it out of the cross product. So we have dq dt times dl crossed with b. And if dt looks familiar, that's because it's actually just current, which is just the rate at which charge flows. So then we can say df is equal to I times dl crossed with b. And keep in mind, this is just for the small charge, so now we can integrate it. So we have the integral of df is equal to the integral of what I just wrote on the right. And then now we should get that F for the magnetic force for a current carrying a wire is equal to the current times the length of the wire crossed with the magnetic field. And keep in mind that the length is actually a vector, and the direction of the vector would be pointing in the direction the current is going in. So if the current is going that way, then this L vector would be pointing in that direction. And if the current is in terms of the length, then you could just rewrite it as what I had earlier, like this. And keep in mind that this is also cross product, and it abides by the same rules as like pretty much any other cross product. So this is the product, and then this I called it F1, or the first factor, and I said this was F2, or the second factor. And yeah, so F1 would just be your index finger, and P, or the product, would just be your thumb, and F2 would just be all your other fingers, or your middle finger if you're more flexible, and they would all be pointing perpendicular to each other. And yeah, so that's how to find the magnetic force for a point charge, and also for like a continuous charge distribution like a current carrying wire. And I hope this video helped, and thank you for watching.